All right, let's get started. Can you guys hear my audio? All right, thanks, Claude. So, good morning, everyone. My name is David Rock. I'm here at the University of Maryland in Baltimore, Maryland, and welcome to Cytometry NR. So, at this point of the course, we have explored substantial portions of how to implement within R a typical supervised, i.e., manual gating style workflow for our cytometry dataset. One important area of this workflow, however, remains absent, namely the section that runs from data retrieval through statistical analysis as well as the creation of figures. So, if you're coming from a more typical immunology style background, this would typically be the point in your workflow where you export the data out of your commercial software to an Excel file, then spend a little bit of time tidying the column names by hand, and then even more substantial amount of time copying and pasting the data back and forth into a commercial statistical analysis software, at which point you're able to run specific tests and then generate some plots showing the relative data and the p-values in the same view. So fortunately, R at its very core is a statistical programming language, which means that it immensely simplifies this process and it can allow us to substantially reduce the amount of time and effort it takes to go from having a gated cell population to publication ready plots. So in this session, we're going to explore how to retrieve summary statistics from the gates within our gating set, how to tidy these outputs and combine them with metadata so we can facilitate statistical analysis and plotting. And then we're also going to continue practicing building functions and leveraging functional programming principles to be able to better speed up our analysis through iteration. So today is going to be a little bit longer than what the normal session is every week. So if you do need to take off at the top of the hour, please feel free and then come back and finish whenever you have time. It is quite a bit of material that really just makes sense to teach in a single go. So one thing to make clear, however, is that this session is not a lesson in statistics. This is not a statistics course. I am not a statistician, nor do I pretend to be. However, for those of you who are interested in learning more about the subject, I do highly recommend two separate resources. One of these is Modern Statistics for Modern Biology by Susan Holmes and Wolfgang Huber. It is really well thought out. It covers a lot of things. It's very beginner friendly. And best of all their examples are in R. And if you're at this point of the R course, I know that all the examples that they show are things that you would actually be able to implement. So I wholly recommend this for anyone interested. I also recommend Statistical Rethinking by Richard McElreath. It's more of an outside Bayesian style perspective to statistics, but it's also a very good, gentle introduction to a modeling course. So it's available both as a book and as a YouTube series that's repeated every year. So I also point you in their direction as far as good resources if you're more interested in understanding what's going on with the numbers in terms of statistics. So, likewise, just because R will allow you to rapidly crank out all the different comparisons and return anything with a p-value that's less than 0.05 doesn't mean that the variable that's being returned is actually relevant to whatever biological question you're trying to study. So science as a whole still has reproducibility crisis, and the statistical test remains exactly that. It's a test. The hard work still remains on the side of the researcher when it comes to understanding complex biology interactions and relating those to the outputs that we get from our statistical tests. So, as we've been doing every week, here's a housekeeping note. I have updated the course repository with all the data, all the functions, and all the little outputs that we are getting from this particular week. So if you haven't yet done so, please go ahead and sync your forked version of the Cytometry and R course on your GitHub. And then once that is done, go in, open up Positron, and pull in those changes to your local computer. If you're following our course organization structure, you would rename it to be week 11, and then you would just be copying and pasting in any additional data sets that you'll need for today in that course repository in your local folder. before pushing those to GitHub so that you are saving all the code that you're working on in case something happens to your computer. For those of you who are more on the visual learning side, I also did a walkthrough tutorial of this exact same process, so you can look at it if you prefer this route. So, as we've been doing for the last several weeks, we need to start off by loading in our data to our GatingSet, and this, of course, starts off by first loading in our libraries. So the packages we'll be using for today are Flow Workspace for all the gating infrastructure, dplyr and ggplot2 for data tidying and visualization, ggcyto so we can visualize our flow plots. We're going to be using OpenCyto when we're creating gates for our data set today. And because we will be iterating through, we're going to be using the per package just so we can gain access to both the map and the walk functions. Now, if we have done all the library calls at this point, we have basically attached packages that contain functions that we're going to need to be able to use later on today. However, over the last couple sessions, we have created our own functions that may also be useful for what we're trying to do. So it makes sense to go ahead and load in the functions that we have created as well. So at the end of the last session, we had created an R folder and placed all our individual function.r files within that folder. So if you just go ahead and copy and paste that folder into your working directory, we can use the combination of the walk function and the source function just to iterate through and activate all those functions, allowing us to be able to work. So how that would look in practice, if you have your R folder within your working directory, you just create a file path to it. You list the files that are present, which are going to be all your function.r files. And then with this list of files that you want to be activating, you're using the walk function from per to iterate through those and then pass them off to source, which will basically attach them to your local environment. So let's go ahead and repeat steps that we would have been doing for the last several weeks, namely finding our FCS files and then loading them into a gating set. So we have a different data set today. These FCS files are still part of Import's SDY 3080 study, which is the cord blood cells in HIV exposure. In the case of today, I went ahead and downsampled everything to be just 10,000 live T cells so that we're able to share it with everyone while keeping in account GitHub's file size limits when it comes to sending data back and forth. However, if you want to do this with your own gating set, with your own data, you can do so. Just remember to change the file path, point it at your files, and then change any parameters that you need. So code is once again repasted from what we had previously. The only change from today is we're going to be generating a lot of PNG files as well as PDFs. So I've created a little output folder where we can store those into later on as we need to. So there's also an output folder path being used at that stage. All right, so then at that point, it's just the same kind of codes we've been running for the last several weeks. We are finding our files, we're loading them into a gating set. Once we have them in the gating set, we're going to go ahead and transform our floor channels with the parameters we have previously optimized. And at that point, since what we're going to be doing today is mostly statistical analysis, we're not only looking at data as far as response variable, but we are trying to designate a column by which we are comparing the groups that are within it. So we need to bring in some metadata as well. So for this particular data set, the associated metadata is as a CSV file within the data folder. So we just need to bring that into R and then attach it to the existing metadata that we can see through the pdata function of our gating set. However, one thing that's different this time around compared to when we've done this process over the last couple weeks is the FCS files have a couple additional zeros. So instead of infant 100, they're showing up as infant 00 instead of the more traditional style we've been seeing infant 100. So we're going to need to do a little bit of data tidying if we are hoping to use the left join function to merge together the two data frames. So what that would look like in practice is we are grabbing our existing metadata from our gating set, creating this little object we're calling current metadata, and then we're doing a little bit of data tidying using both the dplyr and the stringer package. Specifically from stringer, we're using the structure extract and the structure replace functions. And I'll let you play around with this on your own to see exactly how the specimen is changing as far as its names when it's going through these little sections of regex code. But ultimately, it's getting rid of the leading zeros that are present for the sample. And then we're repeating the same process with the metadata that's being brought in. After it's been read in, we're also just making sure it's retaining the same format, at which point, when we have the two data frames, we have a column called specimen, which contains values that match each other on both of the data frames, so we can then use the dplyers left join function to fuse them together into a larger metadata frame that we can assign back to pdata and overwrite our existing gating set metadata. And this is what the code looks like here. And we ultimately end up with a larger metadata where we have specimen, condition, p-type, infant sex as the metadata columns that we could use if we were trying to use them for statistical analysis. So, over the last 2 sessions, we have primarily been using Flowgate when it comes time to set up our gating sets. This is what allows us to open a Shiny app that we can draw gates around our populations of interest. We're going to switch things up a little bit today and go back and use the OpenCyto package, which will allow us to implement automated gates via a template. It's been a while since we last practiced using this back during week 8, and I want to make sure everybody has some continued practice with how to use it. So for the OpenCyto template, since not all these FCS files have already been, so for all these FCS files that we're working with today, I had already exported them out as live T cells as far as the gate that exists. So I'm going to focus most of the gates that are being created downstream to basically identify out the main T cell populations. And since these are the SEB treated tubes, I want to just measure what the cytokine responses for the cells that were present were. Now, things to remember for this data set consists of cord blood specimens. So I kind of expect cytokine responses to already be fairly muted because they are neonatal in nature. And then also, because these were stimulated with SEB, I primarily expect to see cytokine responses for CD4 and CD8 T cells. So if we're gating on V delta 2s and the double negative, CD4 negative, CD8 negative cells, I'm not expecting to get much, if any, cytokine responses measured for those cell populations. So what this would look like, so once again, we're just finding the OpenCyto gating template that I had created that's currently located within the data folder. We're reading this in, and I'm just showing you how it looks right now using the read.csv function. Just to refresh our memory of what an OpenCyto template looks like, we have the alias, which is corresponding to each of the little individual gates that's being created. So you see I'm creating 22 gates in total. As I'm going down, I'm looking at singlets, lymphocytes, T cells, and then I'm doing the plus and minus slash to create both a gate for positive T cells and negative for T cells. And the same thing repeats for the V delta 2s, the CD4s, the CD8s, and on down. And then once I get down and I identify my subsets, I'm going ahead and measuring interferon gamma, TNF alpha, IL-2, as well as cytokine degranulation via the CD107A marker. And for most of these, I'm using the algorithm to allow us to do min density gating, which is basically for a gated area, it selects where it has the minimal density of cells present as the inference location for between where your positive population begins and where your negative population starts. And vice versa, we wanted to do a little bit of gain constraints for reasons we saw back in week 8. So I'm setting gate underscore range is equal to C 2500 and 2750 between parentheses. The reason for this is for some of these specimens, I'm not expecting to see any cytokines at all, given the nature of the specimens. So I kind of want to constrain the cytokine gates to particular locations because that's going to be more where I expect to see them placed at. So let's go ahead and apply the gates. So when we're actually bringing in OpenCyto gates, OpenCyto is expecting us to use the data.table package, specifically its fread function. This is what allows us to be able to read them incorrectly as far as the syntax each and every time. Once these have been read into R, we're passing it to the gating template function, which will basically put them in a list style format that OpenCyto is expecting. And then using the GT underscore gating function, we're actually taking our gating set and applying the gates that we have read in. So previously, when we were back during week 8 and we used OpenCyto, we had been using the GGCyto's package's autoplot function to visualize all the applied gates across all the different cells of interest. However, this was a kind of a generic approach that had several issues that were very apparent very much back during week 8. It wasn't quite zooming in properly on all the different plots, leaving a lot of white space present for a lot of them. This is likely due to a couple outlier dots off the margins that were causing this kind of issue. So when I was first trying to learn how to use OpenCyto back in 2023, I got irritated enough with it that I ended up writing several functions to provide additional visualization tools so that when I was trying to validate whether my OpenCyto gates were correctly placed or not, that I could do so and I could be confident in the results that I would then be using for statistics. So all these functions currently are within my Luciérnaga package, which I'm in the process of wrapping up the documentation for so that I can hopefully submit it to Bioconductor later this summer. So for these examples, since the package is still in beta, I'm also linking to the corresponding .r file. So in case you don't necessarily like how I formatted the ggplots, or if you want to change the variable to account for whatever metadata your instrument manufacturer is throwing at you, you can just modify the files and be able to use them as you desire at that point. So how do you actually go and install a package from GitHub? That's kind of like what we remember back to the very first week of the course. We're using the remotes package. We're using the install_GitHub function. And just like any R package that's based off of GitHub, we are providing the GitHub account before the /, and then the actual repository afterwards. So in my case, it would be David Rock /Luciérnaga would be where we're going to retrieve the R package. And then once that has installed, we're just going to go ahead and attach it to our local environment via the library call, and that will give us access to the different visualization functions. So first off, we have gone ahead and we applied this OpenCyto template, but we need to make sure that the gates that were applied are actually reasonable. And let's go ahead and do that for a first specimen in our gating set before we go back and check for all the different specimens that we are working with today. So the function that we're going to be trying to use first is the utility_gatingplots function, which is going to basically rely on the OpenCyto template that we have already read in to dictate additional plots that are being created and then assembled into a single view. So these can be returned both as a PDF, but it can also be returned to R directly through setting the return type argument to either patchwork or PDF. So what this looks like in terms of syntax is we're passing our first specimen in our gating set, which are being designated through the use of the double square brackets. And then we are giving the function the gates to apply, which is just that read in OpenCyto template. And then right now I just want it returned to R so we're able to visualize what this looks like. So I'm setting this argument first off as patchwork. And this is what it reads into. So you can see my single gate was applied, my lymphocyte gate was applied. It could probably be adjusted in terms of the actual range that's being here, because I'm just grabbing what's probably the more healthy of the T cells, not all the T cells across the board. And then you can see it's grabbing a span of everything on the spark blue, and then it's a fairly more constrained gate being applied for the B delta 2 cells. And this is important, especially when you're working with gates that don't actually have very many dots that are positive, because if it was just min density without any gate constraint range, it might place them here, it might place the line over here, it might completely screw up and just put a gate right through the middle of your negative population, at which point, if you didn't check to see how it was visualized, all of a sudden, it looks like one of your specimens has half of their T cells being gamma delta T cells, which is not a case you would be expecting. Now, one thing that a few of us have encountered over in the discussions over the last couple weeks has been when you're applying an OpenCyto gate using autoplot, those bi-exponential scales you see on the X and Y axis are not the actual numbers that the gate_range argument in your OpenCyto template is using when it comes to applying the gates. So one benefit of utility_gatingplots is the numbers that I see here are actually what's used when it's creating your OpenCyto template. So if, let's say I didn't want to be quite as conservative as I was here, let's say I wanted to move it up right about here. So let's say this is 2,000, this is 3,000. That section right about there would be around 2,750. So I could just update my OpenCyto template for the V delta 2 gate to be somewhere between 2,700 and 2,800. And then it would search that area and find the area minimal density in which it would apply the gate at that location at that stage. So we were able to check for one specimen, and we were able to validate our gates. If we found anything that wasn't quite matching, we could go back to our OpenCyto template, change our gate range arguments for that particular gate, rerun everything to refresh the gates that are present in your gating set, and then continue until you're happy with one specimen. But is there a way we could screen all the specimens in one go so that if it's just an outlier specimen that's not being properly gated, you can identify it and work out some kind of intervention for it. So the good thing of having learned how to use the per package is we can just be able to take this exact same function, iterate it through all the different specimens that are located within our gating set, and just have them return as PDFs being sent to an output folder. And then we could just open and close the individual PDFs to be able to quickly screen through all the different gates for individual specimens without worrying about going back and forth on the little plot view within positron at that stage. So what this would look like in actual practice, because I'm interested in returning outputs that are going as files to the destination, I don't particularly care about them being returned to the R environment. So in that case, instead of using map, I will go ahead and use walk from the per package because it's silent as far as the returned object to R. And then I'm just doing the exact same syntax we've been doing for iteration. I'm doing the .x argument and setting it to the gating set. And as this is being iterated, it's being passed off to our .f argument, which designates our function. And then in this case, I've just went ahead and changed return type to PDF, and I've changed the out path location to output folder. And this is what it looks like after it's finished iterating. We just get those same kind of views of all the different gates that were applied for your individual specimen, visualized as a PDF on a per specimen basis, and all these PDFs are stored in the space that you have designated. And just like I was mentioning, if there's a situation where you realize that for a couple specimens, the gate that's being applied by OpenCyto is just really messing up, it's being placed where it's not supposed to be, you can just go back into your OpenCyto template, update those gate range for that particular gate, rerun it to be able to refresh everything across the board. So one of the benefits of having OpenCyto is it's able to handle a little bit more of the variability between specimens, depending on what algorithm you're using, compared to like the flowgate method where the exact points that you designate are applied across the board for every specimen with no adjustment. The flip side of this, however, is if you set a gate range that's too narrow, like let's say you want minimal density applied between 2500 and 2502, there's only going to be one option essentially, so it's not actually going to be able to account for that variability. So depending on how you set your gate ranges, that can dictate how flexible or how much adjustment you get in the placement of a particular gate. So there's a couple other visualizations that can be useful in the context of checking these OpenCyto gates. So instead of checking everything on a per specimen basis, maybe you're only interested in one particular gate, but seeing how it's applied across all your specimens. If that's what you're trying to do, the Unity plot function is the one that you could be using in this case. It's going to visualize all the specimens that are present within your gating set for a specific population by whichever markers you specified. So in this case, let's say we were interested in seeing what the Tregs look like across all our different specimens that we have acquired. You could just designate your gate of interest as CD4 positive, and then just specify the CD25 by FoxP3 markers on your X and Y axis. So this is what it looks like in syntax. All these functions are very similar in terms of the arguments being provided. In this case, I'm still returning it to R, so that's set as patchwork. But CD25 is our P-Fire 744 floor. The FoxP3 was an index of floor 488. And you can see I'm using the subset of CD4 here in this case. And this is a return that we get back. So right off the bat, if you were trying to just go ahead and also decide what kind of gate range arguments you're doing as you set up your OpenCyto template, you could just run these plots as well, in which case you can see, okay, if I'm setting a gate range for CD25, the transition between the negative cells and the truly positive cells that you would see like in the context of the Tregs are somewhere between probably 2500 here and maybe 2900 for this particular specimen. But then as you look at the other specimens, you can see there's a little bit of non-specific creep going on here. Maybe it's in a mixing issue. So if you set that gate argument in that way, you're going to not exactly be correctly gating for this one particular specimen. So you can evaluate as you go and be able to plan accordingly as far as when you're setting these gate ranges. Additionally, there's a different way of visualizing the same data in the form of ridge plots. Now, this is a one-dimensional style histogram. The benefits are oftentimes you can fill in the histogram portion showing different conditions, like is this coming from a control, a PPD, or an SEB specimen? Is this from a male or female infant? From what time point was it coming? So it's quite useful in the context of a normalization steps as we start trying to fix things in a few weeks. But it can also be used in the context of seeing things kind of on a more generic view for open Cyto templates. So what this is going to look like here is we're using the rigid plots function. We are designating what we want shown on the x-axis. We're designating what's being displayed in terms of metadata on your y-axis. And then what kind of color is being used to fill in the ridges is also a metadata condition at that point. So in this case, I was designating infant sex. So we have male and female. We have CD27 on the x-axis. And I'm having all the different specimens in our gating set being displayed as far as the y-axis. Of course, this is still a one-dimensional view. So, and the other consideration to have for rigid plots is if you have a lot of negative cells and just a few positive cells, the positive cells are going to get drowned out as far as being really scrunched down next to the individual x-axis. But it's a different way of being able to view your same data set as well. And finally, an additional plot that's quite useful is being able to see things as 1/n style plots, which is part of the n/n plots function. It's particularly useful not only when you're evaluating how an unmixing was performed for a particular file, because you can see when unmixing errors occur, but it can also be useful in terms of an actual workflow if you run an n/n for your particular population of interest right before you go and optimize the OpenCyto template. You can visualize all the different markers in a single PDF, and that can give you a cue of like, okay, my initial gate range arguments should be between these parameters for each of the individual floors, and you're better able to account for this across the board. So this is an example of what happens when we return this as patchwork. All these have the option to return an SPDF as well. So we could see for CD62 ligand, if we were setting a gate range, it'd be somewhere in this range. If we're setting it for V delta 2, we could be very conservative and set it right about there. You can see for CCR4, somewhere in this range. 38 and a few of these other markers that are a little bit more of secondary, tertiary markers, you're going to have a little bit more struggle if you're using min density anyway. So these would be the ones that you could watch out for. All right, so all in all, we have gone ahead and used OpenCyto. We've applied specific gates, and everything looks to be roughly gated correctly as for what we are looking at today. However, remember, especially when you do this for your own gating sets for your own data, any gates that are accidentally misplaced at this stage are going to impact your frequencies and your counts that you see for your own data sets. So it's definitely worthwhile visualizing your data that you have used an automated gating algorithm to gate just to make sure everything is actually behaving as you're expecting before you go and put all the hard effort in for the analysis downstream. Because if, for example, you completely messed up your V delta 2 gate, all of a sudden you have 50% of your T cells being V delta 2s, and none of them are actually doing what you expect to for the biology. So things to consider, especially as you do this more frequently and as part of its regular workflow. And this is particularly the case for spectral flow cytometry data, just because any variation that happens at the unmixing stage could result in shifts as far as where your positive and negative populations start and end in terms of the actual MFI value being measured. So while OpenCyto does have the ability to be flexible and account for these differences, it very much is dependent on the algorithm being used when you're setting the method, and then the gate range arguments that you're providing as far as queuing it into what you're expecting for an average individual specimen. All right. So now that we are reasonably happy with the gates that we have applied to our FCS files, we can go ahead and proceed and focus on retrieving the counts and the frequencies for each gate. These in turn, we will need to tidy up just a little bit and then make sure the metadata is arranged correctly to make subsequent steps a little bit easier to implement on our end. So if you remember back to week 5 and then sporadically throughout the function building sessions, we have been using gspop getCountFast function to retrieve the counts that are associated with the individual gates within our gating set. In this case, we also want to go ahead and grab the associated metadata that's being stored within pdata. So we would probably go ahead and use the sister function gspop getCount with meta. That way we can cut down some of the extra steps as far as data tidying two separate data frames together at that point. Additionally, most of the time we're going to be looking at the frequency, so we could just provide that as the argument of return, so we're getting back to frequencies instead of the count and the parent count, so there's less things that we would have to do at that stage. So what this looks like in actual practice, as you can see, we're using gspop get count with meta. We're passing it our gated gating set, and then we're just specifying we want the frequencies returned at that stage. And then what follows that next is just several data tidying steps. Some of these we've seen in the past. For example, population as far as a column returns with a full file path of gating names, which maybe if we're using this for plotting, we just want the actual gate name itself, not all the parent information that's associated with it. When we're returning frequencies, they tend to be a lot of significant digits that are being returned. So maybe we want to round those up to make things a little bit easier, obviously depending on your use case. And then there's a few extraneous columns that are part of the gating set that maybe we don't actually need for subsequent analysis. Maybe they are redundant, in which case we should go ahead and get rid of those if they're not going to be adding to our analysis. And then one thing I will heavily emphasize is the function we're using places all the metadata at the far right side of your data frame. And I just recommend relocating all your metadata columns from the right side all the way over to the left, and just doing so consistently for all your data sets. The reasons for this will become a little bit more obvious a little bit later today as we move through the analysis. So let's go ahead and do this little bit of data tidying. Just as a reminder, we're using base name just to isolate out the gate name itself from the population column, and then we're just writing it on top of the existing column just so that we're simplifying it for ourselves. And we're just going to go ahead and round the frequency column as well. We can just use 2 digits for now just to make it simple. We can then proceed to go ahead and remove the columns that we're not actually interested in. So parent, parent frequency, name, sample name, all these are ones we don't actually need today. So we can specify those to a vector and be able to get rid of them later. And then once we have these as a vector, we can use select function from dplyr. And because we're passing this in as an external vector of names, we do need to use tidyselects any of a helper function to be able to avoid having dplyr return a warning of this syntax is no longer recognized by modern dplyr version XYZ. So once this happens, we get rid of all these different columns that we're not actually interested in. These are now more formatted for what we need. And then the last step is just relocate any remaining metadata columns that contain just characters to the far left side of our data frame at that point. And at this point, our data is going to look something like this. We have a column for specimen. As you can see, the individual specimen is repeated on each row. And then as we go, we have the different metadata columns. And then we get to our population column, which has been cleaned up from the full file paths to now only showing the respective gate name. And then the values corresponding to this gate are shown in the adjacent column called frequency. So as we're looking at this, we can see that for every individual, it will have multiple rows, and that population is representing multiple measurements of data, which is also being tied over to the frequency column right adjacent to it. So in terms of tidying our data, it is tidier than it was, but it's still a little bit unwieldy, specifically because population and frequency don't relate to a single type of measurement, but to multiple types of measurement depending on which row they are in. So many statistical tests are working on the expectation that when you're passing them a column to do the analysis, that within that column, the only thing present is the exact same measurement that you're actually wanting to compare. So the way this data set is currently set up, it's not going to work. So we're going to have to figure a way to basically link together for like the singlet gate, both the measurement from the population and frequency column together, move them to their own column, and then do the same thing for every individual so that at the end of the day, we have new columns that represent each of our individual gates, but that each row represents the measurement for the corresponding specimen. So this sounds complicated, and it is a little bit because there's lots of moving pieces, but fortunately for us, when we're going from a data frame that's very long, having many rows, over to a more wider style data frame that has many columns, there is a package that can help us do this interconversion, and that is the tidyr package. So the two functions that we'll be relying with in this context are the pivot wider function, which is going to take a long style data frame and convert it over to a wider one by changing whatever values we designate into their own specific columns. And then the pivot longer is the same kind of function, but it reverses the process. If you had a wide a data frame that you wanted to make narrow and long, you could do it in that context. So let's first off start by loading in tidyr, because it's not one of the packages we have attached to our local environment. So we can go ahead and use the library call, and tidyr is available via cran. And then at that point, we're going to use the pivot wider. So as you can see, we're passing through our pipe. And because population contains values that designate the individual gates, this is where the new column names are going to be coming from, which is why we're using names from argument, and we're assigning it the population column that's in our current data frame. And then vice versa, the values are currently hiding in the frequency column, with each of them being linked together. So as we're creating the new columns that are specific for the individual gates, we're going to drag the associated values for each individual and place them into the rearranged data frame. So what this looks like actually in practice is we go from where we had a population column and a frequency column, to now having the individual little measurement gates over here with the corresponding values for each specimen being shown here. So we no longer have 4 rows of infant 134. It's just a single row of infant 134, and all the comparisons that were made for this individual are shown as the brand new columns that we created, all the way down to the double negative cells, interfering gamma gate that was drawn. At this point, our data is tidy. It's more in the format that the statistical analysis is expecting, and we are now ready to move on to the statistical testing portion as far as our analysis goes. So, once again, I am not a statistician, nor do I pretend to be one, so it will be overly simplifying here. But when we are working with flow cytometry data, we are typically working with frequencies, so we're taking the count of our cell type of interest divided by the count of the parent gate, times 100 in that context, and then we are generally going to be comparing differences in these frequencies across 2 or 3 groups that are of interest to us, typically. And then generally, the choice of statistical test that we end up using is partially dictated by whether we expect these values to be normally distributed, i.e. parametric, i.e. kind of like a bell curve, or if we expect them to not be normally distributed, i.e. non-parametric. Consequently, we typically end up using one of the 4 tests that we see below. We end up using something like a t-test when we're working with 2 groups. They are, we assume, normally distributed, in which case the test behind the scene is using the means as part of its operation. We may be using a one-way ANOVA if we have 3 groups that we're comparing between, when we assume it's normally distributed, in which case it's also still using means, or the non-parametric version of both of these, in which case it's the Wilcoxon rank sum test when you're doing 2 groups that are non-normally distributed, in which case it's using the medians. And then vice versa, for those with 3 groups, you'd be using Kruskal-Wallis, which would also be in the context of not normally distributed data and using the medians as far as this association goes. So obviously, this is very much a generalization. One of my favorite sentences is statistics as a field didn't end in the early 1900s after they invented these 4 statistical tests. There's a lot of assumptions that go into it. There's a lot of exceptions. There's a lot of edge cases. Our statistician friends have been kept quite busy over the last century finding all of these and writing better ways of doing it. But in general, these are the 4 that we will often see used for a lot of the papers that we end up reading. So one useful way of contextualizing the differences between these different plots is the chart and blog post that was made by Jonas. And I occasionally see this one still circulate around academic circles. It basically illustrates the point that most of the tests that we're using either are linear models or a close approximation of linear models. And that's kind of reflected what we see in the context of R, because many of these R statistical tests are expecting a syntax that's up in the lines of a linear model of y is equal to mx plus b. So when it comes to those arguments, the inputs that we're providing are kind of just basically going to these corresponding slots when it comes to the analysis portion. So typically for most of these R statistical tests that we'll be working with today, it's expecting us to provide the data, i.e. the data frame or the tibble that contains all our metadata and all our measurements of interest. It expects us to provide it a response variable, i.e. the column of data that contains the measurements that we want to analyze to see is there a statistically significant difference in them. And then, because we're going to be comparing things, we need to provide a grouping variable, also known as a factor variable, which is the column that contains the factors or the groups that we're using to do the contrasting. And then, of course, every test will have additional arguments that are able to handle different types of behavior. So there's additional arguments that allow you to specify, do you want a two-sided t-test? Do you want a one-sided t-test? More of the terminology and options you would remember from your intro to basic statistics class at the point. So with this little bit of refresher context, let's go ahead and see about running our first t-test in R. So let's remember what our data set currently looks like after having gone through the pivot wider operation. We currently have our metadata in the first 5-ish columns, and then we start having our different measurements out on the subsequent columns. It looks like we have 30 columns that we're working with today based on the gates that we drew. So when we are going to be working with this in R, we need to know exactly where our metadata columns start and where they end up ending. So if we use column names, we can see all the different column names. And if we look at it right now, we can kind of see as we're going to need to be able to provide the data, the response variable, the grouping variable. So if we are thinking of things that we need to provide, we should think about it in context of this particular data set. So data we already know, we already have it created in our environment, but the response variable and the grouping variable will vary depending on what we're interested in and what we are actively trying to measure at a given point. So in terms of grouping variables, there's two that might be of potential interest today. There's both infant sex as well as the p-type, which is the metadata column that basically designates the neonatal HIV exposure status, where the neonate was unexposed, was HIV exposed but a low, HIV exposed or a high criteria, depending on what the paper documented. So if we look at the unique values that are present within these columns, if we check within infant sex, there's only 2 levels. So we would use this if we're planning to do a t-test or a Mann-Whitney / the Wilcoxon test, or vice versa. If we're looking at our p-type column, it has those 3 comparisons. So that would be more typical if we're trying to use a one-way ANOVA or a Kruskal-Wallis test at that point. And then it's also just a good idea to get a general view of our data as far as the measurement data columns, just so we know if there's any columns that have absolutely no cells present, in which case maybe the test is going to error out and we should plan accordingly for that. So if we run summary on our data frame, you can see the first 5 columns all just metadata, so everything's being returned as type, class, character. But then you can see for the individual columns, everything's being gated. One thing of note is this was gated on all live T cells, but one of our mins is at basically only 50% of the cells are T cells, so I know at least one open cyto gate for the one I shared with you all is off of where it should be for at least one specimen. And then you can continue down. You can see, as we were expecting based on the biology, the V delta 2s in response to SUB are not making any cytokines. If I scroll down, I can see we're going to have a similar situation when it comes to those double negatives where I'm not getting any min or max. Everything's being returned 0. So we might have some issue with those. So, but everything else looks kind of like what we'd expect, and we can expect the t-test or whatever test we're using to actually be running in the background at that point. So let's go ahead and see how we go ahead and implement a context of a t-test. So if we're assuming our data is normally distributed, and it has 2 levels in the group that we want to compare by, we'd be actually using a t-test. Now, for all these examples today, I didn't actually validate whether the data in the columns performing normally or not. This is definitely something that you would want to work through on your own for your own data sets. And this is one of those areas where I'm sure your local statistician would be more than happy to help you not shoot yourself in the foot, depending on what kind of analysis you're trying to do. So if we're starting off with our t-test, in R, it's quite simple. It's just named t.test, so quite easy to do. And the syntax and form of its arguments it's expecting from us is literally the response variable column name, the little tilde sign, and then grouping variable column name right afterwards. And then obviously providing the data frame and then providing any additional arguments that you're providing to it. So what this looks like in actual practice is, let's start off with just that T cell gate. When we put data double square brackets T cells, we're basically subsetting down to just the T cell column. So that's our response variable in this context. Then we're putting a little tilde sign, and then we're repeating the exact same thing for the grouping variable, in which case we're going to be using infant sex. So data square brackets infant sex, we're downsampling to it. And then that's all we really need to run the t-test. But we can also go ahead and specify a few of the additional arguments. We want it to be a two-sided t-test, and we want var equal to be set to true. And at that point, if we hit run, we get this little output return to our console window, where we can see the p-value for this particular comparison was 0.10, and then a bit about the confidence intervals, the means in the different groups as well. So if you were doing this with us at this point, you have successfully ran your first t-test in R, so congratulations. From this output, we can see various bits of information that might be useful to us when it comes to the actual analysis. So while we can parse this output that is returned to the console window by eye, there's a few things that are not quite good in terms of this output. First off, it's not particularly tidy. It's a little bit convoluted. There's a bunch of text. It's not like something that we could easily go in and parse out what the particular p-value was, what the degrees of freedom were. All this information would take us a while to be able to retrieve it in R. So it's not the definition of a tidy data output in terms of what we're working with. However, this is a known issue, so there has been packages that have gone and basically implemented a conversion to go from the standard base R output into a more tidy data format, and this is specifically the Broom package, which is available via CRAN, and specifically its tidy function. So how would this look like in actual practice? Well, once again, after we have attached Broom to our local environment via the library call, we have access to the tidy function, and we're just wrapping that previous line of code that we had inside of tidy and then its parenthesis, which is just going to take the output that's coming from this section of the code and just go ahead and pass it to the tidy function to tidy it out. And as you can see, our return now looks much more tidy. It's everything in terms of rows and columns. And we can see we have a p-value column, we have the confidence columns, we have a couple additional ones to allow us to be able to differentiate the measurements rather than have to parse it from that output. So at this point, we can go ahead and switch around our response variable column name that we're providing just to see what the values for the t-test are for those other columns. So I could check for v delta 2s. I see it's 0.41 for the p-value. I could check for CD4s. It's 0.20. I could check for CD8s. It's 0.8, etc., etc. So I could do this process of basically going into my line of code, going in between these little two square brackets, changing out the name by highlighting, deleting, and then typing in the brand new name. So as you can surmise, we are able to do this, and while it may be a little bit less time intensive than copying and pasting back and forth columns from an Excel file to your commercial statistical software, it's still a little bit time intensive changing the column names, and then also you're risking accidentally deleting one of the square brackets and then trying to run the code and instead getting an error. So there's got to be a better way of not only switching in the individual column names that are of interest to us, but then also to make it a little bit faster for us to do. So the alternative is we could format that exact same line of code that we saw above as its own function, and then be able to specify what we want to use as the response column and the grouping column as arguments within our function, which reduces the likelihood of us messing up and changing the actual code line and getting back an error. So just like we do with any creation of a new function, we're using function and that little assignment arrow to create a new function. In this case, I'm going to call it stats from flow. I'm modifying our current line of code that's running that t-test that's returning as a tidy output. So you can see in place of a actual column name, I'm designating a variable argument, in this case, the column. And then same thing for the grouping variable, I'm saying it as the factor. And each of those are arguments that are being documented within our function. So just like anytime we're creating a new function, we just need to rerun it across the board. This refreshes it in our local environment, creates it, and we are now able to use it. So at that point, if we are running our function as is, we're just providing in data, we're providing a column name, we're providing infant sex, and we'll be able to get our return output. So while editing in a function, as far as we don't have to do as much careful selection and then deletion to replace in the column, it's still on a one-by-one basis to use this and return our t-test value. So it would be better if we could be able to do the same process we've done in the past and be able to iterate in specific columns and then get the returns back and then be able to combine them together and make our own new data frame containing all the results for all of the comparison gates that we're trying to do. And that is where our stats is really, really fun because purrr allows us to do this relatively easy through either the map or the walk function. and then just passing in an actual vector of column names. So first off, let's identify the column names that we can actually use. So if we check column names as it currently is for data, we get back our 30 that we've seen in the past. As we know, the very first 5 are metadata. We don't want to pass a metadata column that just contains characters to our t-test because it's just going to immediately error out. So we want to exclude these from the column names that we're actually iterating through. And that's part of the reason why it's always good just to move them all to the very left-hand side of our data frame, because that way we know they're all in one location. I don't have to worry about an odd metadata column somewhere around column number 78, but then it's followed up by various numeric columns right afterwards. And then if we look at the other ones, if we do n a column on the data frame, it gives us the total number of columns. And then at that point, we know we need to go from column 6 out through column 30. And basically, the way of being able to do this with minimal adjustment required on your end in terms of the start and the stop is basically use encol data, which is going to return the actual final column number, which was 30. And then we can use 6 colon through this value to be able to designate out all the different columns that we're actually using. And because these are placed between the square brackets, this is going to subset out those particular column names. And this was the main reason why I recommended relocating all your metadata over from the right-hand side to the left-hand side, because this way you know you can just iterate from wherever the first numeric column is all the way to the very last one, and that you're not going to be hitting a metadata column by accident in the process. So at this point, we have our column names. At this point, we have a function that's returning a t-test value for us based on the actual response and grouping variables that were provided. We can now use the pers map function to basically iterate through these different column names that we're interested in. And then we can use the apply or spine row function to combine them together into an actual data frame and be able to see all the p-values for all the different gates in a single go. So let's go ahead and give that a shot. So we're using the same thing to isolate out the column names of interest. We're assigning them to these columns. We're using these columns as what we're iterating through using the map function. As we go to the column names, they get passed to stats from flow, which is our function being used. And then we're setting the factor as the infant sex comparison. And sure enough, all these individual rows that are being returned for our 25 different gates are getting bound together. And you can start scrolling down and seeing the p-values for the respective gates. You can see for the v delta 2s where all the data was 0 is returning as NaN, which I had to look up, stands for not a number. So we know it's working accordingly, and then it continues on down the line. So right off the bat, this was relatively quick. It only took like a couple milliseconds to be able to do this process. But one thing as we start looking at this particular data frame is I'm just having all the statistical returns. I actually don't have any information about what column name was being used as our response variable in the part of this test. And then I also don't know what factor was used as the grouping variable for this particular test. So we're missing 2 pretty important pieces of information as far as being able to distinguish which row result corresponds to which gate of interest that we drew. So the way to get around this is we need to go back into our stats from flow function and incorporate in this little bit of additional information to allow us to distinguish the measurement and the grouping columns after the fact when they are bound together into a single data frame. So what this is going to look like is all the arguments are still staying the same. I'm going to go back in here, and remember, as this is iterating in, the column is going to be that first thing returned. I'm just going to go ahead and assign it to gate name, repeat the same process for the factor, and then after our stats are run and we get back our little individual row, we can use the pliers mutate function to basically append these on as new additional columns that contain that value, so that way we have the information that we need on a per row basis. So we can just go ahead and refresh our function by running the code or hitting run code chunk, and then just go ahead and rerun the output lines that we've been using. And sure enough, we still get back the exact same p-values, but if we look down here in this abbreviated slide view, we can see we now have the gate name and the factor name to help us allow us to tell the difference between these 2. And if we look through it and everything looks correctly, we are now good as far as being able to return the outputs for t-test in a really fast manner. But we should probably go ahead and start looking at how to do this if the situation is not something that is normally distributed, i.e. we should go ahead and look at our next statistical test. And this is what occurs in the context of a non-parametric with a 2 levels. So We could, of course, create a brand new function to handle more of our Mann-Whitney or Wilcoxon style tests, but it's generally good if we don't have to rewrite the code multiple times, and if instead we can add additional arguments, additional conditions within the existing function to be able to account for all the different conditions that we're passing it. So let's go ahead and see how this is going to happen in the context of Wilcox. So the Wilcox test in terms of R is being implemented through wilcox.test function. So if you're thinking of trying to integrate it into our existing stats from flow function, we're going to have to be able to specify whether the response and grouping variable are being passed to t-test or if they're being passed to Wilcox test. So at that point, we're going to go ahead and add in a new argument to our function, which is being placed within the parentheses. And remember, we're filling out the Roxygen 2 skeleton as we go, so that if we are trying to remember what a particular argument in our function does 2 weeks from now, when we completely forgot how we initially wrote it, we can just refer back to the documentation and see what is actually being specified. So in this case, I'm designating that extra argument as parametric, and we can define it as either being equal to parametric or equal to non-parametric. And then the rest of the function remains a little bit the same, but we're now using an additional conditional. So if, and then we have the little parentheses. So if the value between the parentheses returns back as true, all the code that's present within the next curly brackets is actually going to get executed, and you'll get the results object returned here. So in this case, if we had set our parametric argument equal to parametric, this is going to be parametric. The double equal to parametric is going to be returning as a true value. At that point, it's going to go ahead and run the t-test and return the output to the results object here. Vice versa, if we had specified non-parametric, this first value here is going to come back as false. It's going to skip over the first set of curly brackets. It's going to run into our next conditional statement, which is else, which is just going to proceed directly to what's contained within these curly brackets, in which case it's going to go ahead and run the Wilcox test and return the output to results. At which point, these two different branches combine in together with each other, and you'd get the appending of the gate name and the factor name to that individual data frame row, and then that's what's going to be returned to our environment at that stage. So let's go ahead and refresh our function and then run our output lines. We can see that this seems to be working well when it comes to parametric, especially anytime you modify a conditional. If it stops working, you're going to get back an error. So checking the different variants of your arguments is the best way of seeing everything's working as expected. And then if I switch parametric over to non-parametric, you can see I'm now getting the Wilcoxon test results returned. So the conditional creation seems to have worked. I didn't mess up my code in any way. I can still get back the p-values for the two respective tests. So we're on a roll in that regard. So continuing on to our next statistical test, what happens if the grouping variable that we want to use to compare our measurement data that is normally distributed, but the grouping level itself has 3 different unique levels that are present within it compared to the 2 we've been working with so far. So that would be a case like if you're using the metadata column for HIV exposure, which was p-type, which has these 3 values being returned. So this is a situation where a one-way ANOVA or a test very similar to it would be quite useful. But is there a way that we could avoid specifying this as an additional argument and also still being able to integrate it in to our existing function, whereby it can just check the grouping or the factor variable, see how many levels are actually present, and then send it off to whether it needs to be going to the t-test or whether it needs to be going to a one-way ANOVA, so you don't have to make all these additional argument specifications. And we can go ahead and do that, but let's go ahead and take this sequentially, little by little, because we're going to be adding quite a bit of moving pieces. So going back to stats from flow, let's first find actually how many levels are present for a given column. So right after we figure out what the factor name is going to be, we're just basically subsetting down the factor. So we just have the values that are present in that particular column. We're passing it to unique, which is going to be able to return to us our individual levels. We just quickly refresh the function. We run our line of code. You can see it's being returned as female male, mostly because I went down and changed return to give us back this factor levels while we're in the process of debugging and troubleshooting. So at that point, we know it is correctly grabbing the levels that are present for our particular the factor column that's being passed in. We can then just pipe it on to length, which is going to return it back as the value of 2. And now we have a numeric value that we can actually use in a conditional statement to basically be able to designate whether to continue to t-test or whether we should continue to a one-way ANOVA. So let's start by just modifying our existing ones to handle the additional argument input in terms of the number of levels, just to make sure it's still working for the more simpler case before we start messing around with the one-way ANOVA. So as we go down here, we're getting this new unique value containing the numeric as far as factor levels. And we're just modifying what we used to have within the conditional statement. So keeping what we already had for the t-test of parametric is equal to, between quotation marks, parametric. And then we're using 2 ampersands in a row to make an additional part of the evaluation. And we're just going to make sure that the factor levels that we're being returned to us is actually equal to 2. So in this case, if we are running a numeric column that is parametric, and it is being compared as far as the group column, let's say infant sex, which is going to return back as true, both this part of the statement is true, and then this part of the statement is true. So overall, this is going to be returned as a value of true, and it's going to go ahead and proceed and run the code between the 2 curly brackets. Vice versa, let's say you ran this on the grouping variable for p-type, so factor levels came back as 3. Even though it is parametric as we specified, the second part of the statement is not true. It comes back as false. And because there's one false value present here, everything is evaluated as false. So that's how it's going to know to skip down past the t-test portion of the code onto the next conditional statement. It will evaluate it. It will see that parametric is not correct. It will go ahead and skip down the next line. So this is kind of a way you can set up a cascade of decisions that it will only proceed and run the code for a particular test if all the criteria is actually being met. Obviously, we just added a little bit of moving pieces with this additional thing. So let's go ahead and refresh the function within our environment by rerunning it, then run our output lines. And even with this modification to the conditional statement, I can still get back my t-test value when this is set to parametric, still using infant sex. And same thing when we're using non-parametric and infant sex, I'm getting back the Wilcoxon thing. So I haven't broken anything into my individual lines of code. Now that this is working, we can go ahead and add in the additional 2 conditional statements that would allow us to do either a one-way ANOVA or a Kruskal-Wallis, depending on the parametric argument that's being specified. So what it's going to look like is here. These are the lines of code that we had just evaluated, that everything was working correctly. We're just adding on an additional else-if statement, and we're doing it a little bit different from what we had it for the t-test. We're just being able to specify factor levels is equal to 3. And because right now we're just in our debugging stage, we want to make sure the conditional statements are working. We'll just have it print a message and assign a value of success to results, which is what's going to be returned to us. And then same thing, we're setting up the conditional statement for if it was going to be doing a Kruskal-Wallis, and just have those same kind of debugging, troubleshooting response messages so that we're able to tell. And then I never like leaving a cascade of else-if statements alone. So I don't want it ending and not being clear if something's not actually working and it's going to fail out in a couple minutes. So I'll always end a cascade with just an else statement. And then the stop function will actually cause an error to be returned to your R environment, which would be your warning sign that something's not quite right as far as what you're expecting. And then you could account for maybe you're passing the wrong style object or maybe something has changed. So we go ahead and refresh our code by running it all again. And we are getting successfully out the stand-in placeholders for the parametric argument when it's set to p-type. So this is where our eventual one-way ANOVA code is going to go. And then same thing for non-parametric, we're still getting back the value right here for success. So the conditional statements are correctly set up. We can now just go in and swap in the code that we need to be able to run these other 2 forms of test. And that process is just, you find the code wherever somebody who has actually dealt with it in the past on the internet is. You just come in and bring it in at that point. So it's very much still in a similar kind of syntax style because of the linear model aspect of it. But you can see for the one-way ANOVA right down here, we have tidy of the output. And then for one-way ANOVA, it's AOV function. And then it's the exact same kind of syntax across the board. And then for the Kruskal-Wallis down here, you can see the exact same kind of syntax being used. It's really just a different test being applied in that context. And then at that point, let's go ahead and refresh our function by rerunning it and check the output line. And sure enough, we're now getting a return value for our one-way ANOVA when we're checking a particular column. and using the p-type as the grouping variable, you can see it's 2 different rows. We have our p-value on the first row, but the second row is mostly residuals. And then if we check it on the Kruskal-Wallis test, we can see there's only a single row being returned, but it's the different values that we associate with it as well. So that values that were just returned for our tree-level comparison test. One-way ANOVA has 2 rows. Kruskal-Wallis has a single row. If you think back to what the t-test and the Mann-Whitney/Wilcoxon test did, they also only had individual rows. So anytime you're working with a function that's returning for multiple types of tests, I always recommend having the format be relatively similar because it allows you to utilize them better in terms of having consistency across the board. So if we were only interested in having a single row for the one-way ANOVA, there's 2 approaches that we could use. We could get rid of the second row entirely by just subsetting down to the first row. The second row was mostly residuals, which may or may not be something that you're actually interested in. On the other hand, if that is something that you want to keep and not actually lose out on that additional bit of information, you could modify your function to basically switch out that second row and put it in as additional new columns so that way no data is being lost, but you still get back everything as a single row. In our context for today, we're mostly interested in returning the p-values as part of the plotting process, so I'll just go ahead and do that first option. So after I'm getting back my results from my one-way ANOVA, I'm using the base R notation of between square brackets 1, comma, to just keep the very first row. That's overwriting the results, and then that is being passed on when it's actually going in and creating the actual information we need for that row. And then at that point, if we start checking, we can see that for parametric, it's all coming back as a single row. I still have my gate name. I can still have my factor name, so I know exactly what was run in this context. Now, typically when you run a one-way ANOVA or Kruskal-Wallis test, you're checking for statistical differences between the groups. It's going to return you a p-value of whether there is a difference between any of the groups. So generally what happens if you do get a p-value that's below your statistical significance threshold cutoff, you're going to follow it up with some kind of pairwise testing, depending on if you're doing a one-way ANOVA or if you're doing a Kruskal-Wallis test. So rather than just getting a yes, this is significant, and then having to follow up separately on individual columns using a pairwise test, what if we integrated in an additional conditional statement that would allow us to run the appropriate pairwise tests directly after the one-way ANOVA or directly after the Kruskal-Wallis, and instead just return the values corresponding to the intergroup comparison at that stage. So what that's going to look like in practice is we will need to have a couple additional arguments. So as you can see, I've updated the Roxygen skeleton documentation for both of these. Our statistical significance test cutoff, the alpha, is just the traditional 0.05 as our default right now, but we allow the ability to be able to change it. And because in R, we're going to be able to iterate through so many different functions in a single go, we do risk the issues of having false discovery. So especially with these pairwise tests, there's the option of applying corrections, things like Benjamin Hochberg and a few additional ones. So if you do want to be able to run them, you need to be able to specify a value that goes to the test correction argument. So I'm just going to externalize out this argument to allow us to be able to specify our own correction being applied. In this case, I don't want to be opinionated in one way or another, so I'm just going to use the none option so that it's not running by default in our context. So at this point, we are only focusing in on the one-way ANOVA section of the code. So I'll come back in here. So this is where we had left off for the one-way ANOVA. We have our single row results. Now, remember, the values that we're going to be getting back from these tests could be values that are significant, being below our alpha cutoff, or they could be things that are not significant, in which case it's still going to be a number. It's just going to be a larger number. Or in cases where it was something like the B delta 2 gates for cytokines where there was no values being passed and the test was not able to run because everything is 0, these tests are going to return either not applicable or NaN, not a number, as a character style return. So we need to be able to handle for all 3 of these conditions in determining whether the pairwise test actually goes ahead and proceeds to run. So obviously, if the value is going to run only in a situation where the alpha is below that cutoff, we can set this section of the conditional statement as when the results, which this is being returned as an individual row in a data frame. So the combination of results, $p-value, is just going to return to us the actual p-value. When the p-value is less than or equal to your alpha, this would evaluate as true, and then this conditional statement would actually run. Now, this would handle the situation of if you get back a numeric value, but wouldn't handle the edge case of if you have a not applicable or not a number or value being returned by the test. So the is.na function basically checks to see is the value not applicable. So if this did return to us as a character value, this portion of the code right here would come back as true, in which case we actually are interested in a situation where it's coming back as false, meaning it's just a numeric. So we can use the little exclamation sign, as we've seen in the past, to flip the condition at that point, making it the opposite. So if this value is coming back as a numeric value, which is what we want, this is going to come back as false, but with the little exclamation sign in front, it's going to come back as a true argument. So when the value is numeric, and that numeric value is below your alpha cutoff, both of these are evaluating as true, so overall, this section here evaluates as true, and then at that point, it's free to run the code that's between the curly brackets. And it's very similar for your pairwise t-test as all the others. You're passing in your response variable, you're passing in your grouping variable, and then as you can see, the externalized argument as far as the adjustment is being entered as that third argument right here. And then this all evaluates over here. We create this new object pairwise. We append the method so that we're able to see that this is not just the one-way ANOVA, it's the next step past it. And then we just assign this to results, which is what's going to be returned by our function. And then we repeat a similar process as this additional nested condition when it actually is evaluating as the Kruskal-Wallis test. Same kind of condition, it's expecting a numeric value that's below the cutoff, and then it just runs the appropriate pairwise comparison for non-parametric, in this case, pairwise Wilcox test, and does the same process all again. So this was a lot of moving pieces. We are going to have to go ahead and refresh the function by running it and then check the output. But for this data set, this is only 10,000 T cells that are all off of cord blood, where I'm not expecting to have much cytokine, and I'm honestly not expecting much differences for the p-type column at this point. So we're likely just to get a bunch of non-significant values being returned to us right off the bat, and we'll never ever be able to evaluate whether the pairwise t-test code is actually working properly. However, since we allowed us to set an alpha, we can set it ridiculously high, something that we would never be doing in actual practice, like 0.99, just to ensure everything is going to come back as being true for statistical significance, and going ahead and proceeding on to the pairwise test at that point. So when we're running our code, everything looks like set up for a one-way ANOVA. We're just modifying our alpha to be able to do it for testing. And as you can see, it did proceed successfully and run the pairwise t-test, and it gives us back the p-values for the intra-group comparisons across the board. And we go ahead and double check for the Kruskal-Wallis by setting parametric also equal to non-parametric, leaving the ridiculously high alpha, and we can see that our code that we wrote is successfully proceeding and now returning to us individual rows for the individual comparisons right there and then. So our code appears to be working just as we had intended it to. So with stats from Flow now mostly set up, let's go ahead and iterate through all the columns and filter for things that may be of interest to us or somewhere in that victim. So if we're doing it in the context of a t-test, once again, we have our t-test columns. We are setting everything up. We're going ahead and use infant sex as a grouping variable. We're setting our alpha much more reasonable as 0.05. As this is being mapped out, all the rows that are being returned are being bound to bind rows. And then afterwards, we're just going to have to apply our filter for anything that is less than a p-value of 0.1. As you see, we end up getting back 3 individual rows. 2 of them are p-values of 0.04 and 0.048 respectively. And then if we went and scrolled, which you can do on the website, you could eventually locate what the gate name is, what the factor name is, and you could go back and evaluate those columns individually at that stage. Same thing repeating for the non-parametric version, just to make sure the code is working. As we can see, we end up getting the different returns. In this case, it looks like some of the cytokines for CD4 and CD8 are coming back borderline. It's only CD8 interfering gamma that kind of looks semi-convincing right now. And just repeating the same process for one-way ANOVA. In this case, we're still keeping an actual alpha of 0.05. As you can see, all these are being returned as individual rows right now, meaning in our entire data set, there was no actual statistical significant value for this comparison. Everything was not quite where we expected it to be. If you did it via Kruskal-Wallis, same kind of story. It's returning us a lower p-value right now, 0.2, but all the p-values are above our alpha cutoff. And then vice versa, if we were trying to just make sure it's working correctly, we could have modified the alpha and tested across the board. So as you can see, we have now written the stats from flow function, which will allow us to, through the specification of the arguments of is it normal, is it non-normal, run all the different combinations of tests that we would need for t-tests for Mann-Whitney/Wilcoxon, for a one-way ANOVA, for Kruskal-Wallis. And through the use of the per package, we can quickly iterate through all the different columns, which corresponds to all the gates that we have drawn, and quickly return back any p-values that may be of interest to us in a single go. Now, whether these p-values are actually interesting and are actually meaningful is a different story, and one that hopefully being able to visualize the data that's generating these p-values will help to clear up. So far, we've been able to iterate through all the measurement columns, returning the resulting statistical test outputs for everybody across the board. So if this was our typical workflow using commercial software, it would be at this point that we'd go ahead and plot the data and then append the p-values that's associated with that individual plot onto the individual groups, but using the little bracket notation as well. So if you remember back to week 6 when we were working with ggplot2 objects, we ended up creating a beeswarm box plot, which was able to compare the frequency data differences between particular groups. While this can be done for individual comparisons, that code that we wrote is pretty much already written. So rather than have to write a completely new function from scratch, rewrite ggplot code from scratch, it'd be much better if we were able to just go ahead and copy in that code, make it a new function, and then just be able to iterate through the columns names just like we did for the statistics to be able to generate out the equivalent plot, the equivalent beeswarm box plot for that underlying data. So let's go ahead and do that. Let's just go grab the week 6 code and copy and paste it into our new function skeleton. So as you can see, I'm starting to add a little bit more of Paroxygen documentation for this particular conditions. And even though we're currently using the double colon notation to specify dependencies, I am listing when I'm using a function that's coming from a different package, which package it's coming from, and then which of the functions is associated with it at that point. And then you can see this is the code that we were using a few weeks ago. It has different layers for both the data underlying layer, the aesthetic layer. It's using both the ggbeeswarm packages, geom beeswarm layer, as well as the geom boxplot geometry layer. And then it has a bit of scale layers to change the way the values are being displayed, as well as some of the theme layers that are customizing the plot across the board. So in the case of our function, there's a lot of because there's a lot of functions that are part of this function that are coming from ggplot2, I'm not going to go ahead and add ggplot2 double colon in front of everything at this point for today. I'm going to instead just go ahead and library ggplot2, just because there's going to be a lot of adjustments and we don't have as much time to go in and add individual ggplot2 double colon in front of all these blue highlighted functions. But in the case of ggbeeswarm, it's only used once, so I'm just going to go ahead and update this dependency that we see right here. So in the context of this function, that's the one I just did, sorry. We'll go ahead and library ggplot2, make it active in our environment, and then have access to all the functions that are within it. So at this point, we have a couple scale aesthetic layers that are present that allow us to basically shape the dots into the corresponding shapes and fill colors designated by the individual metadata column. So we need to go ahead and be able to specify these kind of similar to what we did in the past. And today we're working with infant sex in the p-type metadata columns, so we'll need to have those corresponding values that we can find with those columns assigned out to the particular shapes and to the particular fills. So in this case, for shape sex, you can see I've assigned female is equal to shape 22, and male is equal to shape 21. The individual fillable shapes that we had were documented back during week 6. And then same thing for p-type, I div HU is equal to 22, HU low is 21, HU is 21 as well. And then I'm just specifying the colors that are being used to fill in these particular symbols later on in the plot. And now let's just go ahead and see if our plotting function is still working. So we provide the values in terms of the measurement column of interest and the grouping column of interest. And I'm providing these little vectors containing the actual how they're supposed to shape these little individual dots. And it appears to be working order based off of what we had and remembering back to what we had for week 6. Obviously, there's a ggplot too. We could customize the size. We could arrange how spread out the data is. We have a little bit of customization options as far as the final plot. And then just going ahead and checking our other grouping condition for p-type, we can see HU high, HU low, HU, everything's appearing relatively correctly as how we would want it. One of the personal things, this is an HIV exposure data set. Unexposed is corresponding to HU. Typically, I would have placed them over on the left side of the plot. So if you're trying to rearrange this in something similar for your own data set, the way you would be doing that is through the factor function. So basically, you're doing factor as the function, you're specifying what column you want to change, and then you're just basically providing the sequence of levels. So levels is equal to C parentheses, and then what you want in which order. So HU first, HU low, HU high. And then if you rerun the plot that stage, you can see it's been reordered within ggplot2 as well. And then finally, because this is something that we're going to be iterating through all the different column names, it's important that we're able to tell which plot came from which corresponding column, i.e. which corresponding gate. So it'd be good if the gate name is being placed as the actual title to these plots so that we're able to tell them apart after the fact. So how we actually go do that is we go ahead, we come back into plot. You can see that there's an option to title that had been set to null. We can just set this to plot name, and then as we're iterating in, the column can just become that plot name that's then being assigned. So we go ahead and refresh our plot, we go ahead and rerun it, and then if we go ahead and check, we can see that there's now a title with the corresponding gate name being shown that we're then able to use. So all this seems to be good. It seems to be returning plots that are based on the data that's underlying. Obviously, it's a ggplot2 function. There's additional customizations that can be done. I think I ended up copying just the original version of the ggplot2, not the one we fully customized from week 6. So feel free to tinker with this code to make sure it matches not only your own personal preferences as far as the aesthetics, but then also what it looks like in terms of your own data sets. Now, let's say you had gone in, you put extra effort, you put extra time, you created and customized these ggplots to the point where you're ready to put them into your own PowerPoint or put them into a manuscript. How can you go about exporting these out from R and into a image format, either a PNG, a JPEG, or a TIFF style format? So all these different formats can be mediated by ggplot2's ggsave function. And what this is going to look like in actual practice is something like this. So once we get back our plot that we're happy with, I'm basically doing what we did similar process for when we were creating FCS files last time with downsampling. I am specifying a name that's being built out. Once this name is defined, I'm specifying a location I want it stored to and then placing it in which case I'm specifying the file type through the use of the .png. And then I'm passing all this information about the new storage location / file name to the file name argument. I'm specifying my plot, and then I'm specifying pixel resolution and the size parameters for the image being generated. And then at that point, we get back our image. In this case, I reloaded back into R. And you can do the same process for anything that you think is worthwhile keeping in part of your workflow. So at this point, stat plots for flow seems to be set up. Let's just go ahead and iterate through and get back all our plots for all our markers, all our gated populations of interest. So setting up the syntax for an iteration is very similar to what we saw for stats. In this case, we're just iterating through the columns. And instead, we're passing it to the stats plots for flow function. And then everything else is remaining same except for those two additional arguments containing the shaping vectors that we're using. And at that point, we get back a list of plots. And if we are subsetting down this list of plots, we can see the individual figures that are present. So you can see singlets, lymphocytes, T cells, B delta 2, and so on and so forth. So when you first run this iteration, all these plots are going to be appearing within the plot portion of your window, which is in your right-hand secondary sidebar if you're using positron. And while you can click the back and forth arrows to see all the different plots being iterated, it's much better if you're able to manage to get these all in a more comprehensive view that you can be able to scroll without having to remember which particular specimen, which particular plot are you looking at. And this is where one of my favorite packages in R comes in, namely the patchwork package, which is available via CRAN, which allows you to combine ggplot2 plots together into specific desired configurations, all using parentheses, pipes, and forward slashes, basically to do stand-ins for where does a column start, where does a row start, and vice versa. So we're going to have to use individual ggplot2 plots when we're doing this. So let's break out the list of lists that we had return our plot objects into and just assign them as individual figures by name so it's a little bit easier to track. So in this case, because this is a list of lists, I can specify the individual object. So lymphocytes was our second plot. But I want it to be the actual figure itself, not a mini list. So I'm just using that double square brackets 1 to break it out. So I'm just working with just the ggplot2 object when it comes to lymphocytes. It's similar to the process we did last week when we're working with the cytoset object, where if you put cytoset double square brackets 1, it broke it down to a cytoframe at that point in time. So we're repeating this process for all the different plots that we're actually interested in. And what this is going to look like is, first off, once we have installed patchwork, we just need to attach it to our local environment, which we're doing via the library call. And then once that's done, we can start playing around with the syntax. Let's start with just placing two plots right next to each other. So what this is going to look like is basically this. Like, the first row is being designated by the start and the end parentheses. And then the individual plots are placed where you want them being located. And anytime you're trying to add an additional column, you're just adding a little pipe icon in between them. So in this case, I'm putting lymphocytes on the left. I'm putting the T cells on the right. If I run this line of code with patchwork, you'll see both of my plots are now placed in the larger plot right next to each other. If I want to go ahead and create a second row, I would just put a forward slash immediately after the closing part of the parentheses. And then I can set up and structure a new line being drawn at that stage. So let's say on the second row, I want to place 3 plots. So I do my parentheses for opening and closing. And then I just specify the order of the plots I want to draw based on how they are stored in my environment, putting little pipes between to create the additional columns. And then at this point, if we run that line of code, we get back this more complicated patchwork object, which we're actually then able to use. So now that we have our combined image of interest, how do we go about saving it? Well, we can do very much the similar process to what we just did using ggsave. So this combined patchwork object, we're just assigning it to its own object in our environment, in this case, patchwork image. And with that now created, we just go ahead and use the same lines we did for the saving out. You can see it's now being saved with a slightly different name, and still keeping a lot of the other parts of the code lines the same. And when I do save it, I can notice everything seems a little bit more compressed. Part of this is a much larger object than these individually are, and I still kept the same width and the same height. But as you can see, this was saved as a PNG file, so I would just need to customize the arguments there to make sure everything's still being visualized properly instead of having limited space to work with when it's trying to combine them all together. So overall, this works reasonably well. But in the context of what we're doing, right now, we only drew 25 gates. But I know many of you are going to go out and implement 500 plus gates that are all going to come back as 500 individual plots. So structuring 500 individual plots together on a page by page basis just to generate figures is probably not something that you want to do. So I wrote a little wrapper function that uses patchwork, utility patchwork, which is also in Lucianaga, which basically figures out how many plots are in your list of plots. And then based on how many number of rows and how many number of columns you have specified, just go ahead and adds and creates them in as individual pages that can then be returned as a PDF object to your output folder of choice. So what this looks like in practice, right now, just returning it to our local environment via the patchwork argument. We see it's going to have 2 columns and it's going to have 3 rows. And when I'm viewing this right now in the constrained space of our slide, we can see that, yeah, there's 2 columns and there's 2 rows. And each plot is just being sequenced across the board. And then if I just want to go ahead and return it as a PDF, I just go ahead and change return type to PDF. And then I just go ahead and send it, and it's going to end up there. At which point, opening your PDF and then scrolling through and looking at all 500 plots in a reasonably spaced view is much easier to do and much easier to implement across the board. All right, so we've written two functions, and we've seen how to iterate through and get back all the results of our statistical test, as well as iterate through and get back all the individual plots that are associated with the underlying data. How do we go about combining these two together so that the plots that do have statistical significant results show the little comparison lines and the p-values in the same view? So what we're going to do is basically we're going to combine in the stats from flow function into the modified star plots from flow framework to be able to accomplish this. It's going to be similar to what we did last time when we combined in the downsampling function inside concatenate. So it's another example of a nested function. And this example we'll show today is just more of a rough example. There's additional customizations you could do to make it more polished, but this is just more showing how the process would actually go. So obviously the basic structure starts off by we need to nest stats from flow within the new function that we're creating, make sure that the arguments are being passed in correctly, and that we're able to get out the statistical output just like we would if it had not yet been nested. So what this is going to look like, as you can see, I just went ahead and copied all the Roxygen skeleton from that previous argument in directly here, and just copied in the actual arguments for stats from flow, and we're creating this new actual function combine flow here. And then within the curly brackets of our new function, I'm just pasting the actual line of code that we need to run stats from flow and returning the actual stats object. At this point, I create my new function, I run the output line, and all I'm checking at this point is making sure my p-value is actually correctly being returned to our environment so that we know, okay, we have the values that we would need to add to the plot later on. So the values that are being returned within this results object, there's a lot of information that may not be needed for a plot. We're primarily going to be focused on the actual p-value for the comparison and maybe the method by which that comparison was run. So was it a one-way ANOVA? Was it Kruskal-Wallis? Was it whatever the case may be? So what would happen, however, if the value was non-significant? So if we check right now and see what a non-significant value is going to be coming back as from the Wilcox test, you can see it's going to show back as NaN. So we also need to account for a situation where the value we're retrieving from this initial result may not be numeric, it might be a character. We need to have a way to handle both of these appropriately so that we don't end up with large NaNs displayed on our actual plot object. So we need to consider how to go about when we do that for the extraction. But there is another consideration, namely when the value is statistically significant, the one-way ANOVA and the Kruskal-Wallis proceed immediately to the pairwise comparison test, and they could have one or three rows that either have numeric values that are significant, that are not significant, or that might be coming back as not applicable or NaN as well. So we need to be able to account for all these little different edge cases when it comes time to extract out the p-value so that we can just go ahead and paste it into our ggplot. So one way that we can handle this is there's going to be a lot of values that are going to be not significant. So let's say our alpha value is 0.05. Basically, all the others that are above that point, we could just round them and convert them over to a character value that just shows as n.s, so not significant in our case. In which case, we could just be able to use that to build off of and be able to handle a little bit more. Vice versa, our statistical tests tend to have a lot of significant digits returned on their values. So if you have a value that's 0.04, it's actually going to show as 0.04012568, blah, 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 which might be way too many numbers to display on your plot. So it'd probably be good to write a function that would just round it up to the appropriate number of significant figures and handle anything that's not significant and just call it not significant at that point. So this is an example of what that would look like. So basically, in a situation where your value is greater than your alpha, it's just going to return to us a value that's n.s. And then when it's a statistically significant value, it will round it to the appropriate number. Now, obviously, if you're getting back a value that's 0.0001, we don't want it to round it to 2 significant digits because we're missing out on all that extra significance value. So this is why you can see the round numbers increasing as we go, depending on the values being returned. So when we're actually applying this within a context or a plot, we can remember we're dealing with different types of tests being run. So I'm just retrieving the methods from our corresponding output. And then these methods are structured in characters that are very similar to each other. So we can see that if the condition is going to be a 2-sample t-test or a Wilcoxon rank sum test or whatever variation of it, it's only going to be a single row. So just go ahead and mold the values to make sure they're rounded correctly and return to us that molded p-value out. And vice versa, for a one-way ANOVA or Kruskal-Wallis test, these are the ones that didn't achieve statistical significance. They only returned as a single row. Do the same kind of process of just rounding the individual p-value to the appropriate number of significant figures. And then vice versa, if you did have something that went through the pairwise t-test, you're going to get back individual p-values being returned, in which case you're going to need to individually round each of those. So in that case, we're just using the map function to iterate through, passing them off to a little helper function to get back the correct number of digits. And then we're setting up our edge case of if none of these conditions are met, just return this as n.s argument so that's not causing mischief down the road. And seeing as we just did some major changes, let's just go ahead and validate that everything is still working as we expect. So checking for a t-test, we do have a value that's rounded. If we check for the Wilcoxon, we have a rounded value. If we check for a one-way ANOVA, that's parametric. None of our data set was significant, so it's returning n.s. Checking for a Kruskal-Wallis, same story. It's returning as n.s. And then if we want to check to see what's happening in the context of it did trigger a pairwise comparison, we can do the same testing step we did, set the alpha very, very high, and just see what the outputs look like at that point. So if I change my alpha to 0.99, you see I'm getting back 3 values. All 3 of these values have been rounded. And then if I check it for Kruskal-Wallis, you can see I have 1 rounded value, and then 2 that were above 0.99 came back as not significant across the board. So at this point, we have built out some of the conditional framework to basically round down our p-value to make it an appropriate number of significant digits so it doesn't crowd up our ggplot object when they're combined together. However, as we saw in this case right now with the Kruskal-Wallis, we're getting comparisons between the first and the second group, the second and the third group, and then the first and the third group. And that if we're thinking of each of these values being pasted with its corresponding little bracket lines on our ggplot2 object, we need to make sure these are being placed in the correct location so that we know between which of the groups is this value actually associated with. So we need to keep some bit of information about the index, as well as a little bit of information about the relevant p-values for each of these. So, and then if there's a situation where the value is not significant, maybe you don't actually want to plot a n.s on your plot. Maybe you can just drop them entirely and just proceed as is. In which case, we can use the which function to basically identify these n.s values and then just drop them from consideration, which would leave us with fewer values that we actually want to plot. And then just to keep everything together, we can make a small data frame that will contain our actual values we'll be using later on. So what this looks like in practice, after we do all the molding, we are basically identifying all non-significant values. And this little exclamation sign equals is grabbing the things that are not n.s. So our actual p-values are being retrieved from the data frame, from the vector. And then these are being used as part of these are returning as index locations, because that's how which performs it. So these index values can be used to subset down our existing values so that we only keep the values of interest, and then we're assembling all these into a little data frame. So after we refresh the function by running the code again, and then run our output lines, you can see we're getting back little data frames. Index, meaning this first comparison, the value is 0.04. And if we check on one of the one-way ANOVAs, we can see that when we alter the alphas so that everything looks significant, the value is coming back as index location 1 with the associated p-value, index location 3 with the associated p-value. So at this point, we have positional data as between which of the groups we should draw the lines, as well as the p-value that should be posted directly above those lines. So we have a little bit of the information that we would need to actually go and plot our data. So let's go ahead and copy in the code that actually is generating the beeswarm box plot at that point. So going past where we had left off, just copying and pasting in our existing line of codes, and then modifying any of those additional arguments to handle the situation that we expect to for ggplot2, and changing our return right now to plot just to make sure everything's working. And we get back this semi-ridiculous looking plot for this particular response variable that we're checking. But one thing that's of interest that's worth noting is you can kind of see there's only these little outlier dots that are well and truly above the other rest of the cells being compared to. But if you think about it, we're going to be trying to draw lines and then putting p-values above the lines between these three different groups. So where these lines are going to be drawn is kind of important because we don't want it being drawn in such a way that we're hiding the actual data by where we have pasted our p-value. So we really should identify what the max value in terms of our y-axis is so that any lines being drawn get drawn above it and not placed on top of data obscuring what we're able to see. So how do we go about doing this? Well, we can go ahead and subset for our response data and then just use the max function to identify the maximum value within all the data that's within that column, and then just provide a little bit of wiggle room, maybe like 10% more, so that way it's above that max outlier dot instead of directly on top of the max outlier dot. So how this looks in practice, if we scroll down, we can see we're doing data, square brackets, the column, which is going to retrieve out the values for our measurement data. We're placing it in the max function, which is just only going to keep that main value that's being saved to single y. And then we're timesing it by 1.1 to provide that little bit of wiggle room. In the context of that last plot we saw, the lines would start to be drawn above 0.022. And then at that point, we have the location where we can start drawing the lines based on the index positions where we are going to paste the p-values accordingly. So at this point, we have all the pieces that we need to go into our existing plots and paste the actual corresponding p-values that are actually relevant. So I wrote a little helper function line addition that did this for my Europpe package. It has a lot of moving pieces, as you're going to see in just a couple minutes, and it applies a lot of individual little geom lines to create the little brackets between the groups in a systematic manner. So I honestly recommend just running the code, applying it to our actual function, and then if you're interested in the actual mechanics of this helper function, circle back to it with time, just because it is a little bit convoluted as far as the moving pieces go. Because every time there's a single additional line being drawn, it gets specified as far as X and a Y. So you can look and see how this looks in application in a little bit. But once we have created line addition within our environment, we can go ahead and add it into combine flow. So basically, our plot function is being passed to this helper function. The method information as far as what the test we retrieve from stats is being given. That little p data frame that contains the index and the corresponding p-values is being passed. And then our identified y-axis max is being passed as well. This gets created into a new ggplot2 object, which is being returned. And let's just go ahead and check to see what's happening. So as you can see, it drew this one line, it drew the two little helper lines, and it pasted the 0.04 between the two corresponding groups. If we check it for non-parametric, it's also applying correctly. As you can see, it's appending the test that was run as a little caption directly below. If we check it for parametric, when nothing is statistically significant, it's not actually drawing any lines. It's not showing us any p-values. And same thing for the non-parametric. So all these conditions are working as we expect them to. And then if we force it to look significant by changing the alpha to 0.99, it does go ahead and draw all three comparisons and post the p-values for each of them respectively above where we expect them to be. So that little helper function is behaving as we want to. Obviously, we just need to customize the rest of the ggplot2 so that our dots look appropriate for the space that we're providing. And then same situation, if it was a value that wasn't everything significant across the board, you can see it's only plotting individual lines between the individual groups that are different. All right, at this point, we have combined flow in working order. Let's actually go ahead and take all those column names, iterate through, get back all our plots with all their significance values in a quick and orderly manner. We're going to go ahead and first try the iteration style we've been using for the other two functions, We're specifying the columns going to .x. We're specifying our function as combined flow going to .f. We provide the other ones, we hit run, and we get hit with this error. Argument, the column is missing. No default provided. Well, part of this error is because the iteration has caught up with us, and the syntax doesn't know quite what to do as far as the .x argument. So are we iterating our objects to the column or to one of the optional arguments as well? So basically what we need to fix this particular error is we need to designate out the column as being the destination that we are iterating through by providing it the .x argument. So what this is actually going to look like in principle is we're going to modify what we've already done for iteration just a little bit. So instead of using .f is equal to combined flow and then a comma and then providing the individual arguments, we're going to have it structured where what we're iterating in comes first, so the columns, comma, and then we'll use the little tilde passing on to our function, so combined flow. And rather than having all the different individual arguments being placed right afterwards, after the comma, it will have its own set of parentheses with all the individual arguments and their corresponding values placed inside. But as you can see for the column, we set that equal to .x, which is where we're designating the contents of the columns as they're being iterated into combined flow are being assigned to the column at this point. So we then now try to rerun the line of code, and at that point it runs successfully and we get back our plots. And most of these plots were not statistically significant, so we don't expect to see the values there. But obviously we still have 25 plots. They're all still within our plot window within Positron. It'd be much better for our workflow just to output them to a PDF file where we can quickly screen through them. So that's where we are going to reutilize utility patchwork to do so, combine all our plots into a PDF that will allow us to quickly and easily screen our plots of interest. And sure enough, everything runs. So at this point, we have successfully created several useful functions that allow us to iterate through these measurement columns, returning statistical outputs, plots, or combinations of both. It's important that our work, we can still use these functions again in the future, so we should go ahead and circle through the functions, make sure if it is using a function that's from a different package, thereby creating a dependency, that we're documenting it as we are doing for this first part of the course by putting the package name, :, right before the function name. That way, in case the package is not loaded, your function is still going to be able to run and not error out, kind of like we saw for the last couple sessions. And then vice versa, because later on in the course, we'll be using the import from notation as far as the documentation for dependencies. Go ahead and update the import from tags as well. And then once this has been done and everything's updated correctly, go ahead and copy and paste the individual functions into their own brand new .r files, and then just place them within your R folder within your working environment, so that next time when you want to use them, you just have to copy and paste the R folder to your new project, and then just run the combination of walk and source on the objects within that folder to activate those functions in your environment. So this is a long session, but over the course of the session, we have explored how to retrieve the frequencies from our gating sets, how to tidy the dataset, how to relocate the metadata before leveraging the functional programming capacity in R to iterate out statistical significant testings, results, plots, or both, and then send them to PDF files or PNGs that are much easier to screen within our local environment. In the process, we have the potential to substantially reduce the amount of time it takes us to go from we have validated our gates on our data set to actually seeing the retrieved statistically significant values that might be of interest to us. However, with this vast unleashed power of iteration does come a greater responsibility. Namely, a p-value is not the end-all be-all when it comes to science. There are a lot of caveats that are associated with each test, and I don't want you to iterate through 1,000 different gate combinations, find a single p-value that is of interest, and then go and try to start your science paper based off of a single p-value. Consider this more your opening foray in exploring how to implement statistical functions in R to help your workflow, and that this is a way you can expand your curiosity further and make things a little bit more functional and a little bit more easier on your end in the process. We will be taking a short pause for the cytometry in R course starting next week. So I have tree cyto presentations on early June, as well as some thesis edits that I need to wrap up. And keeping the regular cytometry in R workflow of tree classes a week and writing them on the weekends is just going to be a little bit too much to manage. So we're going to take a temporary pause just so I'm able to do well at all those things, and then also get a little bit of a head start on the next section. So the next section is where we start looking at how to extract out fluorescent signatures, how to compare fluorescent signatures to each other, and how to use them in unmixing. So next time we're going to start working with those mechanics of extracting out spectral signatures from our raw unmixing controls. And then we're also going to see how to apply this in context of being able to pinpoint when an antibody vial that contains a tandem fluorophore is starting to break down, things that you wouldn't otherwise be as easily able to do just looking at the signature on your own spectral flow cytometer. And realizing this has been a very long session, it's nearly 2 hours long. If anyone needs to take off, please feel free to do so. The good thing about today is I am in no shortage when it comes to additional resources. So there's countless good statistical resources by far more knowledgeable people who do really good jobs of explaining from many different angles, from many different statistical flavors and backgrounds. So these are just a few of my favorites that I have relied on in the past, which I'm more than happy to share with everyone. So books, as I've already mentioned, Modern Statistics for Modern Biology by Susan Holmes and Wolfgang Huber. It's really well thought out. It's very much beginner friendly, and all their examples are in R. And they're definitely things that if you're at this point in the course, you would be able to implement for your own workflow. And it's definitely a good place to start for anyone who's interested in it. I also recommend Statistical Rethinking by Richard McElreath. It's both a YouTube and a YouTube series he repeats every year. It's coming from more of an outside Bayesian perspective, which is not as common for flow cytometry, but it's also very much a gentle introduction when it comes to a modeling course. And then Regression and Other Stories by Andrew Gelman is in a similar mold. It's quite useful if you want to start thinking practically as far as some of the considerations, some of the limitations when we're trying to infer evidence for or against something based on a statistical result. And then on YouTube, there's a lot of short content kind of videos, especially related to individual stats topics. These are just but a few that I actually enjoy from Equitable Equations, StatQuest, Very Normal, and Chloe's channel. So they're all worth checking and adding to your subscriptions list, just so if there's new material or there's something that you're interested in, you can always check them out. And then the take-home problems for the next several weeks, I want you to go ahead, take the data set, implement additional open cyto gates, validate that these were actually correctly applied using any of the Luciérnaga visualization functions, primarily utility gating plot. If you do find errors as far as how has OpenCyto implemented this gate, troubleshoot them by providing new gate range arguments until you're happy with your entire data set as far as how it was gated, at which point extract out the data, pass it through combined flow, screenshot anything that looks actually statistically significant where you're like, yeah, I believe that p-value, versus it's one outlier dot driving the entire effect, and you're like, yeah, good thing I didn't just trust the p-value by itself. Second one, we are using the GG beeswarm boxplots, but if you looked at it on the y-axis, everything was less than 1 because we were showing a proportion. So try to figure out how you could modify the stats plot for flow function to instead have displayed your y-axis as a frequency, i.e. as a percentage, and then customize it accordingly, provide additional arguments to give it as an actual option dropdown that you could choose. And then vice versa, in the week 6 material, we had the options of changing the CX and the size of the dots by hand. See if you can figure out how to externalize those arguments just to make the plotting function much more user-friendly for what you're trying to do. And then in some typical immunology workflows, you would run a normality test first, something like a K2 or a Shapiro-Wilks, before implementing whether it's a normal distribution or a non-normal distribution decision on whether you go one-way ANOVA or Kruskal-Wallis. Obviously, your friendly neighborhood statistician may have some very strong thoughts about this field practice. So regardless of what your position on this approach is, it is a good practice when it comes to building out additional conditional statements within a function and making sure all the bits and pieces connect to each other. So see if you can copy and paste the stats from flow function and then modify this new one to add additional arguments for conditional statements so that you could incorporate in directly either the Shapiro-Wilks or the F-Basics packages Omnibus K2 test to see, and then based on that decision, whether you go parametric or non-parametric. So it's a more involved of the tree optional take-home problems at that point. And that's all I have for you guys today. Thank you for your attention. I'm in the discussion page for just a little. I'm on the chat for a little bit, but then otherwise, I'll see you on the discussion page and next time as well.